Hello and welcome to another video presentation courtesy of the University of North Texas Physics Department with the assistance of the Physics Demo Room. My name is Corey Duck and I'll be helping with this demonstration today, which will be talking about the Atwood machine, or a lot of you might know it as a simple pulley. So with this, what we're going to be talking about is balanced and unbalanced forces. So in this case, a balanced force would be as we see right here. We have two objects that are connected by string. The string goes over this pulley, and these objects aren't moving up or down. Unbalanced would be as if one of these were moving and they are accelerating up or downwards. This would mean that we would have an unbalanced force here, and the system is accelerating. So in order to solve for this problem, we have to kind of go back to Newton's second law. So with Newton's second law, remember that it states that the sum of all forces, usually denoted as capital sigma, kind of looks like a weird Z or a weird E, is of the net force is equal to the mass of that object times the net acceleration. Now typically in physics what we do is that we'll usually say the sum of the net force is equal to all of the forces in that one direction, which then equals to that mass times that net acceleration in that direction. But remember that forces are vectors. So in this case, what's going to be really nice is that we're only looking in one direction, which is going to be the vertical direction or the positive y direction. Now, before we even write any of our equations, we look at our system and we say, okay, let's draw the free body diagram for each object, because it's not looking at all of the masses, it's looking at each individual mass. So if we go to the board, you will notice that I have drawn for the first object, is assuming that that object is going to be accelerating upwards, compared to the other one will be accelerating downwards. So with the first object, you see I have FBD subscript 1. That denotes for free body diagram 1, or the first object. This helps me to say that everything with this free body diagram is only for mass 1. So as you see here, I have my axes. I have a vertical axis, which is positive y. I have a negative axis, or I have a horizontal axis that is positive x. You need to help establish this. This is a really good habit to build because it creates great communication to your instructors on what you define as positive. And it also is a good tool for double checking in case you get an answer that doesn't make sense, such as you expect the acceleration to be positive and all of a sudden you get an imaginary number. It tells us that something went wrong and maybe it has to go back to the free body diagram. So in this case, if we just look at one massed object just hanging, and it's just hanging in front of us, we see that we have the strain pulling up the object and we have the acceleration due to gravity pulling down the object. So in this case, we draw the tension pointing in the positive vertical direction, and the weight, which is denoted as M1G, pointing in the downward direction, the negative y. So now if you go to further down the board, we see that we have the sum of net forces for 1 is equal to T, it's positive, minus M1G, because that's a negative force, equals M1 times the acceleration. And I denoted that the acceleration, I believe, is in the positive direction. I didn't necessarily draw it on the axes, I just drew it to the side being going to establish this is what I believe the direction is going to be. Well, then we also do the exact same thing with object number 2, is that we have free body diagram 2 listed. Again, positive x and positive y listed on our axes. We then still have the tension pulling upwards. Even though this object might be going downwards, the tension still wants to pull it up. We still have the mass times gravity, or the weight of the object, pulling it down. And we established that the acceleration is also downwards. So now this goes back to Newton's second law that we wrote the sum of net forces for object 2, subscript 2, is equal to the tension minus M2G equals a minus M2A, not a positive M2A, because we established that the acceleration is downward, remembering that acceleration is a vector. So with this, we can say, well, how do I solve for the acceleration? Well, the easiest way to do this, in my personal preference, is that we solve for tension with reference to mass 2. If we do this by adding M2G onto the right-hand side of the equation, you'll get that tension is equal to a minus M2A. When we substitute that equation into our first force equation, or for object 1, you're going to get a M2G minus M2A minus M1G equals M1A. Now to get all the accelerations on one side, we will add M1A to the right-hand side. This allows us to get this middle equation right here on the board, which states that M2 minus M1 quantity times G is equal to M1 plus M2 quantity times the acceleration. So if we wanted to, we could divide by the quantity of M1 plus M2, and that'll tell us what the acceleration of the system is. So in this case, if M2 is equal to M1, then the acceleration should actually be 0, which is what we were seeing earlier. I had two 100-gram masses attached to a piece of string. They weren't moving anywhere. Oh, I didn't have a change in the overall the system acceleration. Whereas now, if I wanted to, if I put, let's say, M2 is 150 grams, and M1 is 100 grams, I would have 50 over 150, which would be kind of like 5 over 15, because there's an extra 0. Well, 5 over 15, that is equal to 1/3. So 1/3 of G is equal to the acceleration. Well, if the acceleration is approximately 10, it's really 9.8 meters per second squared. But if we say it's approximately 10, that means that our acceleration should be about 3 to 3 1/3 meters per second squared. So what I can do is I can do this in two kind of ways. One way I'm a little bit hesitant of trying to actually do the graphing with it because I don't want the mass to fall on our motion detector. So the other way that we can see is that, okay, well, is this accelerating or not, is actually setting up our little pulley system. So now I'm going to first just put the strings on, because this is like a little bit difficult because of our pulley and just the width of our string. So now what I'm going to do is I'm going to put one of these masses high up, and the other one almost touching the ground. So now what I'm going to do is I'm going to attach a 50-gram mass on one of these objects. And now what I'm going to do is I'm going to let it go, and we should see accelerate. Moves pretty quick. So if we wanted to, what we could do is we could take a motion sensor, and we could put it underneath the one mass that's going to move away from our object, or away from it, and see that the acceleration should be the exact same value no matter what. So if I let go again, I'm slowing it down with my hand to help you kind of see that, oh, it's going to be moving. Even if I was to put it up here, it's still going to move to where this mass will move upwards and this mass will move downwards. So this will be our M1. This will be our M2. Yep, still moved upwards. But if you also notice when we did these calculations, the value of the acceleration I found was still a positive number. That meant that the determination of the direction for the acceleration that we chose was correct. If we got a negative number, it might actually indicate, hey, all the accelerations that you chose were actually supposed to be in the opposite direction. So don't get discouraged if you get a negative acceleration when you expected a positive. This just might mean that you chose the wrong direction initially on your free body diagrams for the acceleration. So thank you for listening for this demonstration today and watching everything, and have a wonderful day.